Hi everyone, my name is Kuvina and welcome back to another video. In the previous sorting video, I briefly explained block sort but saved the bulk of the explanation for later. That's because block sort is, in my opinion, the most complicated sorting algorithm there is. But today I'm going to fully explain block sort, as well as its variants Wiki sort and Grail sort. If I'm made aware of any mistakes in this video, I'll add them as a pinned comment. Also, flashing lights warning. So first of all, why does it have to be so complicated in the first place? When developing a sorting algorithm, there are three main things to consider. Time complexity relates to how long the algorithm takes with input size n. For comparison-based sorting algorithms, the optimal time complexity is O of n log n. Space complexity relates to how much extra memory an algorithm uses, not counting the original list. The optimal space complexity is O of 1, and this property is called being in place. Finally, there's stability. A stable algorithm will preserve the relative order of pieces with the same value. By the way, if you're curious about any of these concepts, feel free to watch the other videos in the series. The holy grail of comparison-based sorting is to find an algorithm that's in place, stable, and n log n. But this is easier said than done. Of the big three n log n algorithms, only merge sort is stable, but only heap sort is in place. If you want an in-place and stable algorithm, then there's insertion sort, but its time complexity is the suboptimal O of n squared. In general, you'll find a three-way trade-off between these properties. Shell sort is a time complexity improvement of insertion sort, but it loses stability. Stability can be added to any algorithm, including heap sort, by assigning each piece an extra value, but this requires O of n space complexity. But what about making merge sort in place? The space complexity actually comes from two different sources. The first of these, recursion, is easy to get rid of using an iterative merge sort. We just have to do all the merges of the same size at the same time. If we call this an iteration, then the sublist to be merged will double in size every iteration. But the main source of space complexity comes from the combine halves operation itself, specifically its use of auxiliary arrays. If we want a type of merge sort to be in place, stable, and O of n log n, then we'll need to use an iterative merge sort with a combine halves operation that's in place, stable, and O of n. Now there is one very specific case where that's easy. If the length of the left sublist is in O of square root n, then you can merge it into the right sublist with an algorithm called rotation-based merging. Basically, you repeatedly use a binary search to find where the first piece goes, then rotate the entire left sublist over there and drop the first piece. This technique is O of n time complexity because each rotation is O of square root n, and that's also the number of rotations. In fact, if the number of unique values in the first sublist is a constant k, then there will only be k rotations. Unfortunately, it's not O of n when the sublists are even, so we can't use it directly for an optimal in-place merge sort. But it will show up a few more times in this video, and it shows the power of square root n. The algorithm that does achieve optimal in-place and stable merging is block sort, and the basic concept is as follows. Instead of merging the entirety of the sublist at once, you break them up into blocks, then rearrange the blocks, and do a bunch of smaller local merges. The two halves will be about equal in length, so if A is the length of the first half, you can use square root A as the block size, and then this will also be the number of blocks for each sublist. This means the total number of blocks is in O of square root n, and the block size is as well. A standard combine halves operation will use O of n time and space complexity. But by breaking it up into two parts, the block rearrangement and the local merging, you can keep the O of n time complexity, but reduce space complexity to O of square root n. With a few more tricks, it's even possible to make it fully in place. The specifics of how this is done can vary depending on the type of block sort. The most popular is Wiki sort. If you hear someone talk about block sort without mentioning a specific type, you can usually assume it's Wiki sort. Another type is Grail sort, but the original block sort from this 2008 paper is different than both of these. There's also square root sort. It has a space complexity O of square root n, which is not fully in place, but it is simpler and a good intermediary step to understand the others. So I'll be covering them in the order square root, original, wiki, grail. But all of them have the same basic outline, so we'll start with that. The first step is to use floor of square root a as the block size. Floor just means you round down, since square root a probably isn't an integer. Using this block size, break up both A and B into blocks. You'll probably have an undersized block for both A and B. You could just place these at the end. You can then ignore the undersized blocks until the local merging. Now it's time for the first major step, block rearrangement. With blocks of the same size, you can easily swap two blocks at a time by swapping the corresponding pieces. Using this technique, you rearrange the blocks into a very specific order. You can determine this order by assigning each block an associated block value. For A blocks, this is the first piece, and for B blocks, it's the last piece. Then you basically sort the blocks by these values in a way that preserves the relative order of blocks with equal block values, which is basically a meta form of stability. This ordering guarantees stability of the individual pieces because if a B block is followed by an A block, it means that A block's block value, which is its first piece, is strictly greater than the B block's block value, which is its last piece, meaning they share no values in common, so there's no risk of reordering pieces with equal values. Now it's time for the local merges, so you have to reincorporate the undersized blocks. You can only merge one A block at a time, so you have to use the following technique. The final block will become a gradually expanding mega block, and you go through the remaining blocks in reverse order with the following conditions. If it's a B block, you simply attach it to the mega block. If it's an A block, then you do a combine halves operation to merge that block into the mega block. You keep going until all blocks are dealt with, and then you're done. Due to the block values being sorted, the first piece in an A block will never have to go into an earlier B block, which is why this works. Also, you don't actually have to merge with the entire mega block. Instead, if you keep track of wherever the first piece of the last A block you merged ended up, you only have to merge up until that point, since you know all of the current A block pieces should go before that. So that's the basic outline of block sort, and as long as both the block rearrangement and local merging steps are stable, the algorithm will be too. But how do these steps actually work, and how can we do them in O of n time? Well, the specifics depend on the type of block sort, so we'll start with square root sort. Remember, the block size is in O of square root n, as is the number of blocks for A, B, and total. Square root sort has O of square root n extra memory to work with, so the local merging is really easy. As we've seen in Tim sort, you can easily merge two sublists in linear time by copying over the first sublist, then comparing those pieces to the ones in the second sublist, and repeatedly putting the smallest piece in place with preference given to the first sublist. The space complexity for a local merge in this case is just the length of the first sublist. That's always just a single A block, so it's O of square root n for a single local merge, as well as for the entire local merging step, since you can delete the auxiliary array after each one. The time complexity of a local merge is the total length. This can actually vary, but it always contains one A block up to one B block and some number of extra B blocks. Due to the way the block values are sorted, the first A piece always goes before the last piece in the first B block after it. So the extra blocks can't stick around for more than one local merge. Therefore, the average time complexity per local merge is O of square root n. This happens O of square root n times, so the local merging is O of n in total. What about the block rearrangement though? It's basically a large-scale merge with blocks instead of pieces and block values instead of piece values. But we can't merge the same way as before, since that would require copying half the list, which is O of n space complexity. So instead, we use a technique called roll and drop. First of all, this is what it looks like. The A blocks stick together and roll through the B blocks. Occasionally, an A block is dropped off and removed from the rolling blocks. To show how it works, we'll look at an example with just the block values. You'll have a current block position L1. Every round, you compare the lowest valued A and B blocks that haven't been dropped, and whichever one is lower, you block swap that over to L1, then drop the block from further consideration and move L1 over. But how do you find the lowest valued not yet dropped A and B blocks? The B block will always be at some position L2, which is always at the start of the group of B blocks, and moves when you drop one. For the A block, you could search through the rolling A blocks for the lowest block value, but there are cases where this might result in a tie. For stability, it's important to pick whichever one of these originally came first, and you have no idea which one that is with this method. So instead, we'll use a technique called movement imitation, which can be demonstrated on this case with many similar value A blocks. Before the block rearrangement, create an array with size equal to the number of A blocks and fill it with increasing integers. These pieces will represent the relative order of A blocks, so whenever you swap two A blocks, you also swap the corresponding pieces here. If the first A block moves past the rest of them, then you shift all of these over. With this technique, you can consult the movement imitation array to see exactly which A block needs to be dropped. When you do drop an A block, you just have to increment a variable to reflect that. This way, you'll always know which A block came first originally, even in the case of ties. The time complexity of a block swap is equal to the block size, so it's O of square root n. Consulting the movement imitation array is also O of square root n on average. These both happen once per block dropped, and the number of those is also an O of square root n, so the block rearrangement in total is O of n time complexity. But the movement imitation array is the only source of space complexity, so that's O of square root n. There's also one last thing I haven't mentioned yet. During the local merging, it helps to know which blocks are A blocks and which are B blocks. This can simply be done with a Boolean array, where a 0 means A and 1 means B. You just have to create this right before the block rearrangement and update it whenever you swap an A block with a B block. With that, we have a way to merge two sublists that's linear time, stable, and almost in place. All we have to do is combine that with iterative merge sort, and we get a sorting algorithm that's n log n, stable, and O of square root n space complexity. Now it's just a matter of getting that down to O of 1, or fully in place. This can be accomplished if you reserve an area of the original array called a buffer and make clever use of the values already there to encode information that would normally need auxiliary arrays. Since square root sort only uses O of square root n space complexity, it means that's also the size of the buffer. So after using it to sort the rest of the list, you can then reincorporate those pieces using rotation-based merging without affecting time complexity. We'll start with the original block sort from this 2008 paper. It was known before then that buffers could be used for theoretically optimal, stable and in-place merging. But I think this was the first time anyone actually made and tested an algorithm for it, and this proved that it wasn't just theoretically optimal, but it was actually practical for sorting. The algorithm works as follows. Given two sublists to be merged with lengths A and B, use floor of square root A as the block size. We'll call this value k. Now you calculate the number of full-sized blocks for each sublist. These are floor of A over k and floor of B over k. Their sum is the total number of full-sized blocks, and we'll call this t. Now it's time for the buffers, both of which are within sublist A, so we'll zoom in on that. First, reserve two areas at the start of the list called S1 and S2, each with a length of t. You want them to share no values in common, so if necessary, introduce a gap g between them to make that happen. S1 and S2 together make up the block distribution storage. I'm not actually sure if it technically counts as a buffer, so I'm just going to call it the basket. After that, you'll have another area called B with length k. This time, you want every value in it to be distinct, so if necessary, simply extract the first k unique values from that point on and move them using rotations. This area is called the buffer. Now you just have to merge whatever is left of A with the entirety of B using the method described earlier. You might notice that in this example, the buffers take up so much space that it defeats the whole purpose of using the block technique. That's because the sublists have to be pretty big before this method is particularly efficient. But importantly, this method is fully in place no matter how big they get. The only reason I'm using a small example is so you can actually see what's happening. But ideally, the number of blocks would still be roughly t. In square root sort, we used a Boolean array of length t to tell us which blocks were A and which were B. But now, we use the basket to simulate a Boolean array. For block index I, you look at piece index I for both S1 and S2. If the second one's bigger, it's a B block, and if the first one's bigger, it's an A block. And if an A block is replaced by a B block or vice versa, you simply swap the corresponding S1 and S2 pieces. With this technique, we've eliminated one of the sources of space complexity. For the movement imitation array, we just have to use the buffer. It's pretty straightforward since we already made sure that all those values are distinct. The movement imitation array is only necessary during the block rearrangement, so when it's time for the local merging, we can repurpose the buffer to help with that. In the past, we would use an auxiliary array and copy the left sublist to it, but we can't do that with the buffer since it contains values from the list which can't be overwritten. But the process is still basically the same, just with swaps instead of overwriting. Given an A block to be merged with some sublist, you start by swapping each A block piece into the buffer. For each of the two sublists, you'll have a current position that starts at the start. Every round, you'll take whichever one is smaller, swap it to its destination, and move the current position and the current destination. After this process, the sublist will be merged, and all pieces from the buffer will have returned there. They might be out of order, but this doesn't cause any stability issues since each buffer value is distinct. So after the block rearrangement and local merging, the list will be sorted except for the buffer, the basket, and the undersized first A block, which we'll call W. So there's one more step of cleaning up. First, restore the buffer and the basket to how they started by sorting the buffer and swapping corresponding pieces in S1 and S2, just put the smaller one first. Now you should still remember where the first piece of the second A block ended up. The area of the sorted list to the left of this will be called V. Then using the last values of S1 and S2, split V up into three parts, V1, V2, and V3. Using rotations, make the list go S1, V1, G, S2, V2, B, W, V3, and then the rest of the list. Now merge W and V3, and then absorb this into the rest of the list. Then do three final merges, S1 with V1, S2 with V2, and B with the rest of the list. You can no longer use a buffer for these three merges, so instead, you just have to use the rotation-based merging algorithm from the beginning of the video. With that, you have merged A and B in O of n time while being in place and preserving stability. Now there are a few cases you have to consider. If the gap G is so long that there's no room for the buffer, then the first sublist is simply S1, G, S2. So you use G to break up B into B1 and B2, then rotate to get S1, B1, G, S2, B2. Then just use rotation-based merging to merge the S1 and S2 into B1 and B2. Another case is if you can't get enough unique values to form the buffer. In that case, however many you did get, that will be the number of A blocks, and you use a bigger block size. That way, the buffer is still enough for movement imitation, but not for the local merging, so you have to use rotation-based merging for those, which is fine because now you know the number of unique values in the rest of A equals the size of the buffer, therefore there's an average of 2 rotations per local merge, saving time complexity. The paper never actually turned this block merging algorithm into a sorting algorithm. I think the best approach for that would be to use iterative merge sort as a baseline, and only for sublist size over 100 do you use the block sort merging algorithm. But even with A and B of size 100, the buffers will still take up half of A, which really does hurt the efficiency of using them at all. Clearly, if we want block sort to be efficient on relatively small sublists, we need a different implementation. That's where Wiki sort comes in. The main difference is that instead of doing block rearrangement and then local merging, it interlaces the two steps. You might think this is worse, because now you need both a movement imitation buffer and local merging buffer at the same time. But doing this eliminates the need for the block distribution storage, which actually took up 80% of the buffer area. So in Wikisort, every time you drop an A block, you have to do a local merge. This means you do the local merges left to right. So we'll look at a weaker example where you're given the block sorted by block value, and you have to do the local merging left to right. It's not enough to simply merge an A block with the following B blocks, since the merge actually needs to go up until wherever the first piece of the next A block ends up within the B block after that. It seems like every merge requires the one after it to be done first, which would necessitate doing them in reverse order. But there's still a solution though. Each local merge can be broken up into 2 steps. First, you figure out where the first piece belongs and rotate the whole block over there. You can then disregard everything behind it and merge the first block with the remaining pieces to the right of it. So what you can do is go through the A blocks left to right, and every round you do the rotation on an A block and then complete the local merge on the previous A block. But even this method runs into issues when you have multiple A blocks in a row. You can get around this by rearranging the blocks in such a way that each A block is now one block to the right of where it would have gone with the normal block value method, and the B blocks shift accordingly. This way, each A block now rotates to the left to be inserted into the B block. So we just have to do the pattern of rotate, then merge the previous one. With that out of the way, we can now get into the actual Wikisort algorithm. It starts by extracting the two buffers. They can go on opposite sides of the list, and each one has a length equal to the block size. You want each one to only contain distinct values. Now you begin the block step. The first buffer is used to track the relative order of the A blocks, but it doesn't use movement imitation. Instead, for each piece in the buffer, you swap it with the second piece of the corresponding full A block. This is called tagging the A block and is necessary to preserve stability in the case of A blocks with equal first pieces. And we swap with the second piece, not the first, since the first piece's value is used during the rotations. Now it's time for the roll and drop step. It works a bit differently than before, and I'm first going to show it without the merges. By default, you'll drop the next available B block, but if the first piece of the lowest valued not dropped A block is less than or equal to the last piece of the most recently dropped B block, then you'll drop that A block instead. This results in the A blocks being one block to the right of where they would be, which is exactly what we want. Remember, the roll and drop step is interlaced with the local merging, so every time you drop an A block, you have to do a few extra steps. After you drop it, you immediately rotate into the B block right before it. Then you take the previous A block and complete the local merge on that one. This might require you to untag it first, and to do the merge, you use the second buffer, which I'm not showing in full here. After all the local merges are done, you just have to put the buffers back using rotation-based merging. This can all get very confusing, so feel free to pause and rewind. I will also show a version that doesn't physically separate the blocks, so it's more clear when pieces are swapped, and this version also shows every swap even for the local merges. Just like before, Wikisort has a special case to consider. If you can't find enough unique values across both sublists to form the two buffers, then you'll only have one buffer consisting of however many unique values you could find. You adjust the block size so that this is the number of A blocks. Then you proceed as normal, but since you no longer have the second buffer, you have to use rotation-based merging for the local merges. This works because rotation-based merging is fast with few unique values. Now we just have to turn this merging algorithm into a sorting algorithm. For that, you start by using insertion sort to form sublists such that the sublist size is something from 16 to 32, and the number of them is a power of 2. This ensures even merges. Now you just repeatedly merge pairs of those sublists using the Wikisort merging algorithm. Every iteration will consist of sublists of the same length, so what you can do is extract the buffers for the first pair, use those to merge the remaining sections of that pair, but before putting those pieces back, you use the same buffers to merge the remaining pairs of that size. This way, you only need to extract new buffers once per iteration. With that, we now have a fully functional Wikisort sorting algorithm. Now it's time for Grail sort. A big difference is that the associated block value is always just the first piece for A and B blocks. This makes the local merging a lot more tricky, but it allows you to have the local merging buffer move along as you do the merges, which looks pretty cool. Now let's get into the specifics. First, you have to calculate the block size, which I'll call K. Grail sort uses the same block size for every iteration, and specifically, K is equal to the first power of 2 greater than or equal to square root n. This means the total number of blocks in the final merge is just T equals floor of n over K. Now you need to reserve some space at the start of the list. It will contain the basket of size T and the buffer of size K. Before even merging anything, you fill the space with all unique values while sorting it. This is actually more space than you need for any merge other than the final one, but reserving all of it right away means you only have to do this step once. The next step is to start sorting the rest of the list with an iterative merge sort, specifically the variety that uses powers of 2, so it merges pieces into pairs, then into groups of 4, 8, 16, and so on. To merge two equally sized sublists, you usually need an auxiliary array with the same length as one of them, but for the iterations where the sublist size is less than or equal to the length of the buffer, you can use the buffer to do the merges. Grail sort has a special function called merge left, where you start with some section consisting of the buffer and then two sorted sublists, and you end with the two sublists merged followed by the buffer. As long as the buffer is at least the same length as the second sorted sublist, this technique will always work, because it's basically what we saw before, but if the first sublist started out already being swapped with the buffer. So on a given iteration, if you're merging sublists of size x, you'll take the last x pieces from the buffer and use those as a buffer for the merge left function. The buffer will move along the sublist and eventually reach the end. If necessary, you can easily move it back to the beginning with a rotation, and then you'll have the full buffer for the next iteration. But eventually, you'll reach a point where the sublists to be merged are bigger than the buffer, specifically exactly twice the size, and you can no longer use merge left. In that case, it's time to use the blocks. Grail sort uses the same block size for every merge, regardless of the length. So the first iteration of block merging, the sublists are broken into 2 blocks, then into 4, 8, and so on. Each one of these merges is actually pretty similar to the original block sort, so let's take a look at one of them. You start by rearranging the blocks with the roll and drop technique. Instead of having a block distribution storage and a movement imitation buffer, Grail sort uses the basket with the combined functionality of both of these. First, you only consider the amount of pieces from it corresponding to the total number of blocks in the current merging step. Since every piece is distinct, you can take the one that corresponds to the last A block and say that anything greater than that represents a B block. Then you can use these pieces to directly represent the A and B blocks, instead of just the relative order like before. Now, every time you swap 2 blocks, all you have to do is swap the corresponding pieces in the basket. There's no shifting over anything. You can tell which ones are A because they'll all be less than a certain value. At this point, the roll and drop step continues as normal, except that the associated block value will always be the first piece of each block. After the block rearrangement is complete, it's time for the local merges. Grail sort does this a bit differently than usual. That's because now, each block might have to be merged with blocks on both sides of it. The process for the local merges involves a slightly different merging function than before, called smart merge left. Basically, when you merge 2 sublists, the resulting sublist will either have a bunch of A values or a bunch of B values at the end. I'm going to call this the bonus area. Smart merge left makes sure that the ending configuration is the merged list, then the buffer, and only after that the bonus area, which can be from A or B. This is necessary because the bonus area might be needed for future merges, while the other section won't be, and the sublists to be merged are always to the right of the buffer. In Grail sort, the sublist to be merged might actually be a B block on the left and an A block on the right. But no matter what, you always prioritize pieces from A in the case of ties. With that, we can now look at how to do the local merging step as a whole. You start with a buffer followed by a bunch of A and B blocks. A and B are what I'm going to call the block types. You start by considering the first block as bonus. Then you go through each remaining block with the following conditions. If the block type is the same as the bonus area, you add the block to the bonus area. But if not, you do a smart merge left operation to merge the bonus area with that block. You keep going until you reach the end, and for the final merge, you just use regular merge left. With that, you've merged the 2 sublists. Now you reset the basket, and the buffer is now in position to merge the next pair in that iteration. You keep going like this to finish the iteration, then you put the buffer back for the next ones. Since the block size and sublist size are both powers of 2, the only risk of undersized blocks is at the very end, so we'll look at an example like that and also show all the swaps. After the final iteration, you'll have a sorted list except for the buffer and the basket. So you sort those, and then simply merge those pieces into the rest of the list using rotation-based merging. Now, Grail sort also has cases where you don't have enough unique values for the buffer. If you find the list contains fewer than 4 unique values, then you simply sort the whole thing with an iterative merge sort where you use rotation-based merging. If there are more than 3 unique values, but still not enough for the buffer, then you take the number you could find, then use the biggest power of 2 less than that, and that will be the buffer size. You can use it directly for the first few iterations of the iterative merge sort as a buffer. Once the sublists are larger than the buffer, you have to switch to block merging, which is a lot more tricky this time. For each subsequent iteration, you set a very specific block size so that the number of blocks doesn't exceed the number of pieces in the buffer, and you use that as the basket for this step to rearrange the blocks. Now you just have to do the local merges, which usually requires a buffer, but since we have so few unique values, it means we can use rotation-based merging and it still has the same time complexity. With those cases included, the Grail sort algorithm is now fully functional. And with that, we've covered square root sort, the original block sort, wiki sort, and Grail sort. But even still, there are so many intricacies of these algorithms that I can't cover today. For example, how do you make these adaptive? They are very optimal both asymptotically and experimentally, but adaptability is an important factor for whether people want to implement these algorithms. When making something adaptive, there are just so many little tricks you can do that it's kind of beyond the scope of this video. But adaptive versions of these definitely have been made, and a lot of work on the whole idea of block merging continues to this day. In fact, Wikisort was named as such because they wanted it to be a collaborative effort that was continually added to. And Grail sort has a less subtly named improvement called Holy Grail sort, where one of the improvements is that the buffer can also move right to left. If you want to learn more about these, you can find resources in the description. With that, we've reached the end of the video. It's not easy to wrap your mind around these algorithms, but I hope that I've helped. Make sure to like and subscribe if you want to help the channel grow. Thank you for watching, and I'll see you next time. Bye.